The topic of surface energy, surface tension, contact angle, and wetting are presented here in a single chapter. As we will see, this is appropriate given how strongly these topics are interrelated. The first lecture will review surface energy and surface tension, beginning with the description of surface energy based on the loss of molecular interactions. This explanation, which tends to be popular in chemistry circles, provides a connection between observed experimental values and physical bonds which occur in the bulk region. Many overstate this connection's utility, given the nebulous nature of chemical species at surfaces and interfaces. A more detailed thermodynamic analysis provides the basis for a useful predictive expression for interfacial energies, utilizing surface energy values for the pure components composing the interface. The second half of the lecture focuses on the mechanical description of surface forces, or surface tension. Using the surface tension description greatly simplifies explanations for how various test methods gauge its magnitude. Let's clearly define the terms surfaces and interfaces. As mentioned previously, an interface forms between two immiscible phases, which have been assigned arbitrarily as phase alpha and phase beta. The molecules that compose the two phases are immiscible in each other. This observation does not necessarily mean that the phases are pure. This can be mixtures of different chemical components or species of different sizes or architectures such as polymers. It also does not imply that no dissolution has occurred. It merely indicates that no further net movement of species occurs, and the two regions have distinctly different properties. As we move out of alpha and into beta, intensive properties such as density, melting and boiling points, conductivity, and so forth gradually change from values for the bulk alpha phase to those for the bulk beta phase. This region over which properties are in transition is the surface or interface. Although we often treat this region as a sharp demarcation plane, in reality it can be of appreciable thickness on the molecular scale, and its thickness may be dependent on the property of interest. By convention, when one phase is a condensed phase, that is a liquid or solid, and the other a gas or vacuum, we refer to the region between the phases as a surface. When both are condensed phases, we call it an interface. However, the term interface is considered more general. The region between two immiscible phases is a region with unique properties, usually very different from those of the phases that lead up to it. The interface, or more appropriately the interfacial region, particularly in liquids, is highly unstable. So unstable that it will take any opportunity it has to eliminate itself as much as possible. This effect is apparent in the definition using Gibbs free energy, known as the surface free energy in dimensions of energy per unit area, and most commonly reported in millijoules per meter squared. This definition tells us that the surface free energy must be greater than zero for an interface to exist. If it were negative, a spontaneous expansion of the surface area would occur, resulting in complete dissolution. The equation also tells us that surface area contracts spontaneously. In other words, interfaces exist even though it is not energetically favorable, because they have to. Hence, the time spent by a molecule at a liquid interface tends to be fleeting, and molecules at solid surfaces tend to be markedly more reactive due to their desire for change. The integration of the equation results in an expression for calculating the reversible work with an increase in surface area. We can use this to estimate the work required to expand a soap film stretched across a wire frame of dimensions L by X. One side of the frame is movable. We calculate the work required to expand the wire frame a distance delta x at constant temperature and pressure as the final area minus the initial area multiplied by the surface free energy. The factor of 2 is due to the two-sided nature of a soap film, which consists of liquid trapped between two liquid air surfaces. We should be aware of the thermodynamic nature of this calculation. As discussed, thermodynamics is an equilibrium field. Thus, the calculations are for the change in the system, specifically the increase in surface area, regardless of the path taken. In other words, there are many ways to arrive at this increase in surface area. The calculation above provides the minimum work to achieve the increase. A quick note on notation. Gamma subscript ij is used throughout this course to denote general surface and interfacial free energies involving solids, liquids, and vapors. For surfaces in contact with the surrounding vapor, a single subscript identifying the liquid or solid is sufficient. Keep in mind that this convention is not always followed. Here, we will try to use the more explicit notation as much as possible. For purposes of examining thermodynamic properties, a common approach for modeling a surface or interface is according to Gibbs. This convention treats the interface as a two-dimensional plane, which provides a clear demarcation between phases. The approach is unrealistic in that the surface region is several nanometers thick. However, it is quite useful and is analogous to the approach we reviewed for modeling solute dissolution into a solvent. In this case, we could define an ideal interface as one in which the phase's properties are assumed constant right up to the dividing plane. For example, an intensive property X on a per mole basis is assumed constant throughout the alpha phase all the way up to the Gibbs dividing plane, and it is assumed constant throughout the beta phase starting at the plane. Properties for the surface are the difference between X's total value for the heterogeneous system and the intensive values assuming an ideal interface multiplied by the number of moles in those phases. We define the value as the plane area multiplied by the excess surface value, an intensive property on a per unit surface area basis. To be clear, this is the leftover portion assuming an ideal interface. We find that the surface free energy is the excess surface free energy if we use this convention to define Gibbs free energy for a heterogeneous system. It is the convention to adopt the former terminology for the thermodynamic quantities of the interface. Here we provide Gibbs surface free energy in terms of enthalpy and entropy, which defines the surface enthalpy and surface entropy values. Differentiating this expression with respect to absolute temperature provides a useful equation relating the derivative of the interfacial free energy versus temperature plot to surface entropy, which indicates that this quantity can be gauged experimentally. The surface enthalpy is equal to the total surface energy plus pressure multiplied by volume. For the Gibbs approach, the surface is a plane and has no volume. This result allows us to write the surface free energy in a form that will help with our molecular contributions analysis. Next, we will examine surface free energy from a molecular point of view, beginning with the total surface energy. For this, consider a pure liquid in equilibrium with its vapor at a constant temperature and pressure. We can write the heterogeneous closed system's internal energy as follows, which provides a relationship with the total surface energy. Based on this relationship, we will estimate the total surface energy by evaluating the potential energy change for a single molecule to move from the bulk region of the pure liquid to the liquid surface. We begin in the bulk region of the pure liquid. Here, the molecule is surrounded by like species. To estimate the total interaction energy of the molecule, we assume that only the nearest neighbors make a significant contribution. Each interaction is equivalent, and the energies are additive. These provide an expression of the bulk interaction energy in terms of the number of nearest neighbor interactions and the interaction energy at the bulk equilibrium bond length. We use the same approach and assumptions for estimating the interaction energy for the molecule at the surface of a liquid. These provide an expression for the surface interaction energy in terms of the number of nearest neighbors and the interaction energy at the equilibrium bond length. Next, we assume that the equilibrium bond lengths in the bulk region and the surface are approximately the same. The change in the potential energy of the molecule is the difference in the interaction energy between the surface and the bulk region. We divide this value by the area the molecule occupies at the surface to estimate the total surface energy. From Chapter 1, we know how to estimate the interaction energy from the heat of vaporization at the temperature of interest, making this a seemingly useful result. However, the fractional loss in interactions and the area occupied by the molecule at the surface strongly influence this equation and are challenging to estimate. Surface free energy decreases with temperature, and plotting surface free energy for a pure liquid against temperature tends to produce a straight line with a negative slope. This slope is the surface entropy for the measurement temperature. Values are usually greater than 0, indicating that molecules at the surface are more disorganized than in the bulk region. An initial review of the data also indicates that larger, more flexible species have lower surface entropy values when compared with smaller, more compact molecules. The table shows values for the surface free energy, total surface energy, and temperature-weighted surface entropy. Unlike the discussion for the dissolution of organic species in water, there are a few hard and fast rules for comparing pure materials' surface free energy. Indeed, water retains a certain degree of its hydrogen-bonded network in the liquid state, which provides for a high heat of vaporization and a high surface free energy relative to other organic liquids. However, for other organic species, it's usually not so clear-cut. The table contains examples of homologous series of both normal alkanes and normal alcohols. It can be seen that surface free energy increases with increasing molecular weight, but the increase is relatively modest. Comparisons of these groups show that the addition of a functional group capable of providing for hydrogen bonding in the pure state increases the surface free energy for the same size alkyl group. However, N-hexanol, which is larger and has a significantly higher heat of vaporization, has a lower surface free energy when compared with toluene. The handful of results listed make the point that the surface free energy is strongly dependent on chemical family. The more general point is that it's difficult to predict and compare surface free energy values given the complexity of the interactions at interfaces. Next, consider the interface between two organic liquids, say oil and water. Again, we carry out the same analysis to determine the total surface energy. However, in this case, it is a bit more complicated. The formation of the interface requires the movement of a molecule in each phase to the interface. Thus, the interaction energy at the interface is the sum of interactions with like species and interactions occurring across the interface with molecules from each other phase. The total change in potential energy is the sum of the differences in interaction energy between the interface and the bulk for a molecule from each of the phases. We assume that the same number of interactions for molecules occur in both phases, and both have similar bond lengths at the interface and in the bulk regions. This approximation produces an expression for the total interfacial energy. It is written here in terms of the total surface free energy for the two pure phases and the interaction energy between the molecules across the interface. The interaction energy between different molecular species is problematic. There is no physical property that can be used to predict this. To get around it, we make two assumptions. We assume that the total interaction energy is equal to the attractive energy, and that the interaction energy between different species is equal to the Berthelot relation. With these approximations, we can rearrange the equation for estimating the total interaction energy from the total surface energy of the pure phases composing the interface. This equation is useful for estimating total interfacial energies, but it is even more helpful in that it provides an approach for estimating thermodynamic potentials at the interface. By analogy, we can write an expression for the interfacial free energy in terms of the surface free energies of the phases composing the interface. We've added a correction factor, which provides useful information regarding the interactions at the interface. Here we rearrange the base equation. The left-hand side is the theoretical or reversible work of adhesion. It is the work required to separate phase alpha from phase beta. For a pure phase, the work required to separate it from itself, the work of cohesion, is equal to 2 times the surface free energy for that phase. Thus, the right-hand side is the averaged work of cohesion for the alpha and beta phases. Phi is thus the ratio of the work of adhesion to the averaged work of cohesion. If interactions across the interface are the same as in the pure phases forming the interface, phi is equal to 1. If they are less, which is more likely, it's less than 1. If they are stronger, which is relatively rare, it is greater than 1. The table lists the surface free energies for various organic liquids, along with the interfacial free energy when these liquids form an interface with water. Also listed are the phi values. In most cases, this correction factor is less than 1. The exception here is one that we've seen before. The ether cannot form hydrogen bonds in the pure liquid. However, such interactions are present across the interface with water, resulting in stronger interactions at the interface versus the average level of interactions in the pure states. When no data are available, authors will commonly assume phi is simply equal to 1. Before leaving the topic of interfacial free energy, let's review a convenient method for measuring it. The spinning drop technique is accurate down to about 10 to the negative 6 millijoules per meter squared, and it's a technique that's useful for systems such as microemulsions, which we'll talk about later on. Now, the early equipment was restricted to such applications due to limitations in the angular velocity. However, modern equipment allows for angular velocities greater than 1500 radians per second and is useful for surface and interfacial free energies up to about 50 millijoules per meter squared. The technique involves the injection of a liquid drop of density ρL into a higher density liquid ρH held in a cylindrical capillary tube, usually of diameter of maybe 0.1 to 0.2 centimeters. Rotating the tube at an angular velocity omega causes the low density drop to locate axially at the tube's center. With increasing omega, the drop deforms from a sphere to a prolate ellipsoid, and at high enough angular velocities to an elongated cylinder. We arrive at the equation for calculating the interfacial free energy by minimizing the mechanical energy for the cylinder with respect to the cylinder's radius, noting that the drop volume is a constant. Minimizing the cylinder's mechanical energy with respect to radius results in the Vonnegut's equation shown here. The problem here asks us to use the interfacial free energies listed between organic liquids and water to estimate the required angular velocities to measure these values. We can assume a drop volume of 200 milliliters, an L over RC value of 10, and a water density of 1,000 kilograms per meters cubed. Now, after finding the organic liquids densities, we apply the Vonnegut's equation to determine the angular velocities. It appears that the higher the surface or interfacial free energy, the greater the required angular velocity. As noted, modern commercial equipment can be operated at angular velocities greater than 1500 radians per second, making the method useful for a wide variety of systems. At this point, we will pivot slightly to address the topic of surface or interfacial tension. Surface tension and surface free energy are essentially describing the same phenomenon, precisely the tendency of surfaces to contract to reduce their size spontaneously. From a mechanical perspective, we can think of the surface as a thin skin or membrane that separates adjacent homogeneous phases. Its contraction manifests as a force that acts perpendicular to its boundaries and parallel to the surface plane. We define surface tension as the magnitude of the force per unit length of the boundary. For now, we will denote surface tension with a prime. For the schematic shown here, the resulting magnitude of the force just acting on this wall of length L is equal to the surface tension multiplied by L. The direction of this force is perpendicular to the wall and parallel to the liquid surface. This is a quick example to reinforce what we just reviewed. It asks us to decide which arrangement can support the greatest weight. Strictly applying the definition for surface tension, the force acts perpendicular to the surface boundary, which in this case is a movable wire, and parallel to the liquid surface. Hopefully you can see that this is a soap film, so it's two-sided. If all the films are the same, the max force for all of them is equal to 2 multiplied by the length of the movable wire multiplied by the surface tension. So the answer is E. Let's discuss the molecular origins of surface tension. We spent some time discussing the movement of a single molecule from the bulk regions of a pure liquid to the surface, resulting in the loss of stabilizing interactions, which gives rise to the total surface energy. Another way of looking at this process is that the balancing forces for a molecule at the surface are absent, resulting in a net force pulling it back into the bulk. We already know that this force is proportional to the decrease of potential energy when it descends. As the molecule is pulled back towards the bulk region, It acts like a pulley system, transferring the vertical force into a horizontal one. The action of millions of molecules doing the same is what gives rise to the surface tension. The same qualitative explanation applies for interfacial tension, with the difference being that the balancing forces are weak rather than absent. Thus, interfacial tensions tend to be smaller than surface tensions. We could say that there is less tension on the pulley line. The relationship between surface tension and surface free energy can be a little bit confusing. A good analogy is the relationship between interaction energy and forces for a pair of interacting molecules. Either can be used to describe the attraction and repulsion between them. These quantities are related. One is obtainable from the other. While the interaction energy is a scalar quantity, the interaction force is a vector quantity, with the force direction always being along a line that connects the centers of the interacting chemical species. To demonstrate the equivalencies between surface tension and surface free energy, we return to the SO film, which is stretched across a wire frame of dimensions L by X, with one edge of the frame being movable. Surfaces will minimize their areas spontaneously, so a force must be applied to the wireframe's movable edge to prevent it from contracting. The minimum work required to expand the film a distance delta x using the surface tension approach is the surface tension multiplied by 2L delta x, or surface tension multiplied by the increase in the film surface area. Using the surface free energy approach, we find that the work is equal to the surface free energy value multiplied by the increase in the film surface area. We conclude from this that the surface tension and surface free energy are equivalent quantities, but are used to approach the problem from different perspectives. These quantities will have the same magnitude for the same system, but oftentimes use different units. We usually report surface tension in millinewtons per meter. That's a force per unit length acting on the surface boundary, with a direction that's perpendicular to the boundary and parallel to the surface. We usually report surface free energy in millijoules per meter squared, and is the work required per unit area to expand a surface at a constant temperature and pressure. For the same system, these quantities will have the same magnitude. Gauging surface behavior from the mechanical perspective makes it easier to describe some of the techniques used in its measurement. One of the most straightforward approaches, at least in theory, is the drop weight method. The technique estimates a liquid's surface tension from the maximum weight of a drop supported by a narrow capillary of known radius. In practice, the measurement is made using a syringe needle or heated and stretched glass pipette of known outside radius, R. The test involves slowly feeding a liquid through the capillary. Usually multiple drops are collected and weighed. The average maximum weight of a single drop that can form at the tip of a capillary is related to the radius of the capillary and the surface tension of the test liquid through Tate's law. This approach is convenient, but it lacks accuracy. Obtaining an accurate drop weight is problematic because only a portion of the drop breaks free from the capillary tube's tip. We can establish a correction factor for a specific liquid in setup. This correction factor correlates with the capillary radius ratio to the cube root of the drop volume calculated from the liquid density. Note that the correlation factor is often significant. Here we describe the Wilhelmy plate method. The measurement involves bringing a small plate with a perimeter of tens of millimeters into contact with the test liquid. During testing, we attach the plate to a sensitive load cell, which is zeroed so only the force due to the plate's interaction with the liquid is being measured. Tensiometers usually raise the test liquid up to the plate and allow for monitoring of both the force and plate position. The force reads 0 until the plate gets close enough to the surface that the liquid can climb up on it. As mentioned previously, a liquid surface will apply a parallel tension to anything it attaches to through a wetting line. Typically, we make measurements using a Wilhelmy plate composed of a roughened platinum, which has a large surface free energy around 1700 millijoules per meter squared. This allows for complete wetting by organic liquids. As a result, the tension force is pulling straight down on the plate along its perimeter. As we lower the plate into the liquid, it experiences a buoyancy force pushing up. A plot of the measured force versus plate position allows for extrapolation of the force on the plate to the value where it is not influenced by buoyancy. This is the force value used to calculate the surface tension. The Wilhelmy plate method can also be used to measure interfacial tension. Another popular direct measuring technique of surface tension is the Denoy ring method. The same principles are at work as described for the Wilhelmy plate experiments, but the technique differs in more than just the test sample's geometry. Here we begin the test by fully submerging the tared ring into a test liquid, and during measurements, it is pulled back through the liquid surface. We calculate the surface tension from the maximum force measured during this process. While this eliminates buoyancy's influence on the measured force, a correction is required to account for the liquid absorbed and carried on the ring. As with the Wilhelmy plate technique, the wire is typically composed of platinum, allowing for complete wetting by organic liquids. An advantage of this technique is that it provides a greater wetting line length because both the inside and outside of the wire ring are wet. However, a complicating factor with this method is that the maximum force tends to be reached on the ring's outside perimeter first. Various approaches exist to correct for this, which are part of software packages that accompany modern tensiometers. We can also carry out this test using a solid rod or wire, known as the Denoy-Padé method. This approach avoids the need for the correction, but does not provide for the extended wetting line length. Also, the Denoy ring method is an effective means for gauging interfacial tension. We will end our first lecture here. Our discussion's objective was to portray the surface not only as a separate phase, but also as a region with unique properties, which included a discussion of the molecular forces that give rise to such properties. We then transitioned into the topic of surface tension, allowing for more intuitive descriptions of surface characterization techniques. The next lecture discusses the contact angle. Unlike the situation described here, where the surface runs parallel to the boundary, such as the surface of a platinum Wilhelmy plate, surfaces more typically take on a non-zero angle at the contact line. The contact angle determines the direction of the tension force, which can provide for some unexpected behavior, as discussed later in our chapter on capillarity.